SwayamPrabha. Digital India. Educated India.
We have come to the last lecture of week 9. In this, let us have a recapitulation of the non-equilibrium flow across normal and oblique shocks. Then we will spend a little time studying nozzle flow, blunt body flow, and a very interesting concept, binary scaling. So, these are the things we plan to cover in this lecture. This is something that we had discussed in the previous lecture, but it is a very important concept and therefore, it needs to be recapitulated once again. This was the non-equilibrium flow behind a normal shock, which we tried discussing with an illustration here. And you find that we have a normal shock front, and behind that normal shock front, we have marked a few regions, region A, B and C respectively. And it is worth noting the significance of each one of these regions. As we had discussed earlier, that the region A is a rather short region just behind the shock front, where the properties of the flow are essentially frozen, followed by a region B, where it encounters non-equilibrium phenomenon that is of a moderate length. And then you have a very long region practically extending to infinity beyond the region B, the region C, which we have marked, where the flow attains equilibrium. As the fluid particles move downstream of the shock front, the finite rate reactions take place. Due to the finite rates of the chemical reactions, the flow properties would relax towards their equilibrium values. And when we keep this picture in mind, the shock wave encompasses both the shock front and the non-equilibrium region immediately behind the front, followed by the equilibrium region, which would come out later. And if you consider that there is a diatomic gas which encounters this kind of a situation, where it is diatomic oxygen in our case here, then in front of the shock wave, that means in the upstream region, region 1, the mass fraction of oxygen in terms of its atomic form will be 0, and in terms of its molecular form will be equal to 1. The properties immediately behind the shock front would be obtained from frozen flow results using gamma equal to 1.4. So, that is essentially a calorically perfect gas approximation that we use, and subsequently the non-equilibrium will proceed. That is basically the broad concept. If you try to show the spatial variation of the different important aspects like mass fraction, static temperature, density, etc., you will find that there is a certain length over which the changes occur, the relaxation length, so to say. And we have the Hugonot conditions applied across the shock, and the frozen properties behind the shock are essentially obtained from those jump conditions, followed by the non-equilibrium conditions which exist over the length scale, which is shown by a double arrow. Subsequently, the equilibrium region which follows. The dissociation is associated with a drop in static temperature and a rise of density. When it comes to oblique shock wave flow, then it involves a little further complication, and if you recall, we dealt with two cases. One, had a curved compression corner geometry, in which case we said that we could have a straight attached oblique shock, while there could be another situation where you have a straight compression corner with a certain fixed angle theta a, but in which case we have a curved attached oblique shock. These kind of happenings were not known to us when we looked at the theory from the calorically perfect gas point of view, which we have learnt earlier, but when it comes to non-equilibrium flow, we have to get used to these surprises. The idea was that in the encircled region, we have pointed a bright red arrow, and that basically indicates that dissociation continues along that direction behind the shock as the flow crosses the shock and approaches the body. And you may recall that non-equilibrium flow is associated with scale effect, and that means there is a length scale which is important over here to influence the way the flow behaves as long as the non-equilibrium effects are significant, and therefore, more the length that you allow, the more it moves towards an equilibrium situation, the less the length that you allow it, closer it is to a frozen flow condition. Therefore, close to the start of the compression corner, we find that the flow essentially behaves like a frozen one, but more the length that we allow behind the shock up to the body, more the effect of non-equilibrium, till you allow enough length which is sufficient to take the flow to equilibrium flow conditions. And that happens essentially through a change of theta, the compression angle, as we can see in the case of a curved wall, which would induce a straight shock. We would discuss about this aspect further in the subsequent slide here. If we do not provide the adjustment of the flow deflection at the wall to accommodate the non-equilibrium flow behind the shock gets curved. Since we had provided that adjustment of flow deflection in the previous slide, we got a straight shock. Note that if we were looking at it from a calorically perfect flow or chemically reacting equilibrium flow point of view, the shock would remain straight in both the cases. For a given deflection angle theta, the equilibrium shock wave angle is always less than the frozen shock wave angle. So, the extremes are shown over here. Different shock layer thicknesses are encountered as we move along the wedge. The least shock layer thickness occurs at the leading edge and the most as we move towards the trailing edge. Therefore, the shock layer experiences frozen flow near the leading edge and non-equilibrium flow as we progress towards the trailing edge, and far downstream from the leading edge the flow attains equilibrium conditions. This is, as I mentioned earlier, manifestation of the scale effect in non-equilibrium flow. You may recall in the previous lecture we had mentioned that chemical reactions do not affect the conservation of the tangential velocity component across the shock or even in the non-equilibrium region following the shock. In the inviscid case, it is more true. However, the normal component of the velocity varies along the shock normal direction. This is essentially because of the dissociation phenomena. And of course, if you look at the normal component of the velocity, the jump occurs between Vn1 and Vn2, that is basically the Hugoniot conditions that apply as far as the perpendicular velocity component is concerned. In the non-equilibrium flow behind the normal shock, density increases with distance behind the shock. Similar thing happens in case of oblique shock too. Because rho Vn is a constant for flow across a normal shock, Vn must decrease with distance behind the shock wave. The same thing happens in the case of an oblique shock too. Therefore, you expect that the Vn3 that you have here closer to the wall will be lower than the Vn2, which is a little upstream, and therefore, this inequality works. In order to have a straight oblique shock, as we mentioned earlier, we would have this kind of a inequality connecting the three compression angles that we can see at the different locations along the compression corner. The final outcome is the streamlines in non-equilibrium flow behind a straight oblique shock are curved, and they continuously increase their deflection angle until equilibrium conditions are reached far downstream. Therefore, this inequality. In order to create a straight oblique shock front in a non-equilibrium flow, we have to have a compression corner that is shaped like a curved solid surface. We have taken note of that. We have taken note of the changing deflection angle, and the curved non-uniform flow field in the non-equilibrium region behind a straight oblique shock front is definitely an important difference that we saw compared to the familiar uniform flows obtained for calorically perfect or equilibrium oblique shock results. In this figure, we have shown the two possibilities that you have an equilibrium chemically reacting gas flow, or you can have a calorically perfect gas flow, and therefore, the frozen case, which corresponds to the calorically perfect gas flow, has a higher wave angle compared to the equilibrium case, and the mixed frozen non-equilibrium equilibrium regions have intermediate shock angles, which depend on the local flow conditions, which would range anywhere between these two angles, which are the extreme cases. And since from one location to the other along the shock front, the non-equilibrium will persist, therefore, the beta will continuously keep changing, giving rise to a curved oblique shock if you have a constant angle at the compression corner, like the way we have shown it here. We are trying to sum up the findings again. The non-equilibrium flow behind the shock wave varies with distance behind the shock. This introduces the dimensional scale. The non-equilibrium length scale or relaxation distance is defined as the distance downstream of the shock required for flow properties to reach 95% of their equilibrium values. For any given flow, the relaxation distances are different for different kinds of flows, which depends on the geometry of the flow and of course, also on the thermodynamic variables. Non-equilibrium distances behind a normal shock are much smaller than behind an oblique shock for the same flight conditions. And we need to note here that higher temperature and pressure behind a normal shock for the same upstream conditions lead to the higher reaction rates, and this is the primary reason behind the difference. Higher reaction rates would mean what? That equilibrium is reached within a shorter time, and hence in an advective or convective flow, this happens over a shorter distance in a normal shock compared to an oblique shock. This difference in non-equilibrium distance is a manifestation of difference in relaxation distance for two different flow field features, which is nothing but the normal shock and the oblique shock for the same upstream conditions. So, this is what we meant by different for different flows as far as relaxation distances are concerned. This is a brief recapitulation of the solution techniques for frozen, equilibrium and non-equilibrium flow. Solution of frozen or calorically perfect flow behind a shock wave, which could be normal or oblique, involves separate algebraic relations for different flow and thermodynamic variables. Solution of equilibrium flow behind a shock requires coupled numerical solution involving a system of algebraic equations. Variation of gas properties as a function of temperature and pressure has to be incorporated into these calculations, and this is of course true also for non-equilibrium flow calculations. Solution of non-equilibrium flow behind a shock wave requires numerical solution of differential equations. Why is this? It is because the non-equilibrium flow introduces a length scale into the flow, and the solution of such flows can therefore be treated only by using differential equations. So, this was a brief overview and recapitulation of the normal and oblique shock non-equilibrium flow once again. Now, we move on to CD nozzle flow, which may be occurring in different situations like in rocket nozzle or in high enthalpy aerodynamic testing facilities, that is the hypersonic tunnels. And if you are venturing into obtaining Inviscid solution through a CD nozzle, it can be used, it can be obtained by using the method of characteristics or by solving Euler equations, and we try to model the expansion of a high temperature gas through a nozzle when vibrational and or chemical non-equilibrium conditions may prevail within the gas. And why we are interested to simulate such conditions and check in advance before we really want to deploy such devices is because in a rocket nozzle non-equilibrium effects can have significant detrimental aspects like decrease of thrust and decrease of specific impulse, which are extremely vital performance parameters for a rocket nozzle. While in a high temperature, high enthalpy wind tunnel, the non-equilibrium effects make the flow conditions in the test section somewhat uncertain to predict. In most non-equilibrium nozzle flows which occur with high temperature, high enthalpy gas, the following conditions apply. As the flow starts expanding from the reservoir conditions, which are essentially the stagnation pressure and temperature, the equilibrium conditions for the vibrational energy and the CI exist in the converging portion of the CD nozzle, which is basically the reservoir to the throat. The flow remains frozen from the throat in the diverging portion of the nozzle. So, this is the usual behavior. The above can be explained as follows. The dissociated gas mixture undergoes equilibrium chemistry in the converging portion if the reaction times are lower than the flow time due to the rapid cooling caused due to the expansion, due to the high pressure ratios which are usually involved. Beyond the throat, the flow often remains frozen. However, if it is a fast reacting gas, for example, if it is hydrogen for example, non-equilibrium may exist downstream of the throat too, and it may happen for other gases too under different stagnation conditions. Therefore, there is no straightforward answer to this kind of a complex flow. The general rule is that non-equilibrium flow should be solved throughout the length of the nozzle, and the flow solution finally would reveal the extent of non-equilibrium existing along the length of the nozzle. The final outcome depends on the gas mixture composition at stagnation condition from where it starts expanding, the downstream conditions at the exit of the nozzle as well as the nozzle geometry. So, we do not have a straightforward solution really. However, the picture that we tried to portray over here is a general picture which may apply in a number of situations. In terms of interpreting such solutions, we need to revisit the concepts which we discussed earlier, the concepts which distinguish frozen, equilibrium and non-equilibrium flows. So, we recall that the reaction rates the way they behave for frozen flow or equilibrium flow, as well as the vibration relaxation times are important. And it depends on whether the flow will respond to the changes which are happening locally as it moves across the flow, or it would remain inert or dormant to it. If it responds extremely quickly, then it would always remain in equilibrium locally as it flows through the flow field, and non-equilibrium conditions will lie anywhere in between the two extremes, for which the characteristic length scale of the flow field L and the local velocity, the scaling between the two matters, because if you take a ratio of the two, it typically gives you an estimate of the residence time of the fluid particle in the flow as it moves through the device, which we termed as the fluid dynamic time. Correspondingly, there is the chemistry time, where the energy exchanges within the internal energy modes occur, as well as the chemical reactions get completed, and it depends on how these two temperatures scale that we have to finally take a call whether it remains frozen predominantly or in equilibrium predominantly, or is going through a non-equilibrium. It applies for a CD nozzle, it applies for a blunt body flow, or any other kind of geometry that you can think of. So, these are the primary issues that one has to consider before coming to a conclusion, and therefore, to be on the safer side, it would be reasonable to solve the flow as a non-equilibrium one, and then try to figure out that in which regions it is predominantly behaving like a frozen one, behaving like equilibrium one, and also behaving like a non-equilibrium one as a mixed regime. Coming to inviscid high temperature non-equilibrium flow over a blunt body, we have tried to mark the main regions of interest over here. Due to the shape of the blunt body, as we know, we have a detached bow shock wave and a small standoff distance lying between the shock and the nose of the body. Typically, this is the leading edge of the body or the nose of the body, and we have marked a stagnation streamline which is meeting the leading edge, and the leading edge acts as the stagnation point. We have marked it as equilibrium flow here. Again, we have marked an equilibrium flow somewhere downstream over here. We have intermediate regions where non-equilibrium flow and frozen flow also have been marked. An interesting region is the sonic line, which is dotted here, and we need to understand the behavior of the flow field and the corresponding nature of the chemical reactions which occur in the gap between the shock and the body, which is the shock layer. Proceeding with that discussion, in the nose region, the chemical composition resembles that in the non-equilibrium region behind a normal shock wave, immediately behind the normal portion of the bow shock. So, we expect that it would start behaving like a non-equilibrium region, like the way we studied there. However, there is a very important fact which sets it aside. As it is the stagnation streamline, the flow will get compressed and slowed. It ultimately reaches 0 velocity at the stagnation point. If we follow a fluid element along this streamline, we will observe that it takes a very long time for the fluid particle to traverse this distance, essentially from a point like this to the stagnation point. And this consequently means that the local equilibrium conditions would exist at the stagnation point anyway, because the flow time is way larger than the chemistry time, and therefore, you can expect that the flow will be highly dissociated, even ionized, if it is a strong shock, if you follow it along this stagnation streamline. And therefore, that is the reason why we have marked this region as equilibrium flow. If you look at the region of interest which is shown through the red curved region, then we need to discuss what is going on there. We observe that the fluid elements above the stagnation streamline would show these kind of behaviors like the way we have noted here. The flow expands rapidly downstream of the stagnation point. The surface streamline encounters very large pressure and temperature gradients in the region near the sonic point. So, the flow is rapidly accelerating as it moves along the surface towards the sonic point. So, the sonic point is essentially where the sonic line meets the body here. And we need to note very importantly that in inviscid flow the tangential velocity component at the wall is non-zero, because it is the slip condition that we refer to, and the pressure and temperature gradients for the coordinate running along the wall, if we name it as S, then these derivatives are large negative quantities. That means, there is a very rapid drop of static pressure, a rapid drop of temperature as you follow this profile along the body surface and you approach the sonic line. The above flow field behavior is similar to the non-equilibrium flow through a CD nozzle, where it was mentioned that sudden freezing of the flow can occur downstream of the throat of the nozzle. Because the flow times are extremely short, the chemistry times may not be able to keep pace with the flow times, and therefore, it essentially gets frozen in terms of chemical reactions. The same kind of sudden freezing can be experienced near the wall sonic point. The surface of the body downstream of the sonic point can be essentially bathed or wetted in a region of nearly frozen flow. Since the streamline started with a large amount of dissociation and ionization at the stagnation point, which we already discussed, this frozen flow is characterized by a thin region of highly dissociated and ionized gas that flows downstream. It is unable to change its properties because it is essentially frozen at that kind of a mixture of species. Finally, we come to the very interesting phenomena of binary scaling. For non-equilibrium processes involving two body molecular collisions, an interesting and important scaling can be obtained from non-equilibrium flow fields. This scaling is called as the binary scaling. We assume that the dominant chemical reaction is caused by dissociation. Here we are talking about dissociation of molecular oxygen, and the collision partner is generically represented as Cp, and that leads to dissociation of molecular oxygen to atomic form. And in the above chemical equation, the dissociation occurs from the left to right, and it is a two body process essentially. The reverse reaction, which can occur from right to left, is recombination. It is a three body process because you have two here and one here, and has lower probability than the dissociation reaction. We make a few assumptions here that the dissociation reaction is the primary one, recombination is entirely neglected. We talk about steady flow and two dimensional flow. Now, based on these assumptions, the species continuity equation for atomic oxygen can be written in a form like this. You have learned the species continuity equation earlier, you have to recall that, and then the rate term can be represented like this in terms of the Kf for this dissociation reaction. And you notice that this can be finally expressed in a form like this, where you have a constant which is a function of temperature, and then you introduce a number of non-dimensional variables for the different lengths, the velocities, the density. you define the blunt body nose radius as capital R, and the free stream properties of the flow are of course defined as rho infinity u infinity, which are important parameters for us. We will see that once the above equation is non-dimensionalized, it gives rise to a form like this. Now, if you see, we have a very interesting group here, rho infinity r by u infinity, and let us consider two different flows which are occurring with identical values of u infinity and t infinity. In that case, the two flows may involve different values of rho infinity and r, but if the product of rho infinity and r happens to be the same. So, let us say rho infinity 1 times r 1 is the same as rho infinity 2 times r 2, then the numerator becomes the same for the two flows. U infinity anyway is maintained the same for both the cases, and then the two flows will essentially become similar in nature. Now, where does the similarity mainly manifest itself? We see the similarity in the CO plot in terms of the running coordinate S following the point just behind the shock up to the stagnation point, scaled by the radius of the blunt body. So, you have two blunt bodies, one with radius r 1, the other with radius r 2, which is just double of r 1, and you find that the approaching flow has identical u infinity t infinity, but the rho infinity from the upstream flow differ. In one, with the r 1 radius case, rho infinity is rho 1. With the r 2 blunt body case, the rho infinity is rho 2, which is half of rho 1. You notice that incidentally the rho 1 r 1 equals rho 2 r 2, which means the rho r being constant condition has been maintained for both the cases. In that case, we will have identical curves for the two blunt bodies for the CO distribution, as long as your x axis is obtained through S by R 1 for the first blunt body, the one on the top, or S by R 2 for the second blunt body, which is at the bottom. This is what we mean by the binary scaling concept. As long as the flow field associated is dominated by the two body dissociation reactions rather than the three body recombination reactions, which are the backward ones, the different cases which ensure that rho r product is identical, the results would exactly fall on top of each other. And if the ratio K f by K r is much larger than unity, then anyway this condition will be fulfilled. Let us sum up. In this lecture, we recapitulated the concepts of non-equilibrium high temperature flow through a normal shock and oblique shock. We learned the concepts associated with non-equilibrium high temperature flow through a CD nozzle and also across a blunt body, and we finally close by learning about binary scaling. Thank you.